So let's take a look at several options for an acquisition function that tells us how to, or which sample to sample next, right? How to choose the next sample. So this is something that we've seen before. We can either exploit or explore. So exploit would be to prefer points with high expected mean value, right? Usually closer to points that we already know about. And explore means to prefer the points with high variance. These are usually points that are further away in the kernel space from points that we already sampled, right? So this can be tied back to the exploit-explore problem that we discussed previously. And so our acquisition function should balance between exploiting and exploring. We're going to quickly discuss 4 different common acquisition functions. One is the probability of improvement, the expected improvement, the Gaussian process upper confident bound, and finally we're going to discuss Thompson sample. So I'll quickly go over these different acquisition functions. Probability of improvements attempts to compute, well, as the name implies, what is the probability that a specific sample will improve over our currently best known sample. Okay, so it of course can derive that by the Gaussian that is assumed around each one of the points. We can use those to do statistical inference regarding the, well, as I said, the probability that sample will come from that sample will produce higher values compared to the best known values so far. So this is our first acquisition function that we'll discuss. Another common one is the expected improvement. So this one is not only trying to compute the probability, it's not trying to compute the probability of improvement, but by how much this sample is expected to improve over our currently best known sample. Okay, and again, because we have such simplifying assumptions regarding the Gaussian structure, the normal distribution around each point, we can also use common statistical tool to compute not only the probability of improvement, but also the expected improvement. Finally, this is something that we've seen before, the UCB function, the upper confidence bound. We can apply it also for this case, for Bayesian optimization case, and compute the bonus, the variance dependent bonus to each expected mean value for each one of the points in our space, and choose the one that maximizes the upper confidence bound prediction for that point. Okay, so how do these different acquisition functions compare to each other? So here we can see a simple example. By the way, each one of these acquisition functions has a hyperparameter that needs to be tuned. And of course, different values for these hyperparameter values will produce different performance. But let's look at just a single example. So let's say that this is our target function. And we currently have 4 sample points. And of course, we have large variance around for points that are far away from those that we actually sampled. But still we have some prediction, some mean prediction and variance prediction around, well, any point in our space. As I said, those points that are further away from the known points have obviously higher variance. And now you can consult each one of your acquisition functions regarding which sample should be drawn next. So you can see that most of them agree that the new function should be drawn from somewhere in this range, right? Taking into account both the mean prediction, which is the black line, and also the uncertainty, which is the shaded blue area. While probability of improvement slightly tends more towards the currently known best performing sample, right? You can see it here, specifically with the higher epsilon values, or not epsilon. How is this parameter called?
Sigma.
Sigma, the highest sigma values. The expected improvement also tends to agree that this area is more expected to produce higher improvement, but you can see that the expected of improvements tends towards the more uncertain region, and the UCB actually, specifically with a high V, with a low V values, a high V value, right, the red line, actually gives higher preference to the higher uncertainty, right? But with a lower V value, you can see that it still provides more preference to the higher expected mu, the higher expected mu. So this is also an example performance, but over several iterations. We won't go over this now, but here you can see the different acquisition function, probability of improvement, expected improvement, and UCB. But now, how they perform over several iterations. So the first sample, the second sample, all the way to the sixth sample. Which one, by the way, performs best, Vaibhav?
I think it's GP-UCB.
So let's see. Yeah, so first of all, this one, probability of improvement, actually converges on a suboptimal value, right? While I guess both expected improvement and UCB were able to converge on the optimal value at about the same speed, right? But in any way, right, the better option is actually domain dependent, and in some cases probability of improvement might work better, and in other, well, in different cases each one of those might outperform the others. Finally, I would like to discuss one more acquisition function that is well, slightly different, and it's very popular. It actually works very well, and it also allows you to, I would say it's more intuitive, and sometimes it's easier to implement, and it works very well. And this is known as Thompson sampling. So what we do here is we sample a function from the Gaussian process, right? Where the function is sampled as a set of f stars along the entire state space, and it is drawn by the Gaussian process that is inferred for each point, right? So for instance, I'll start by sampling a value for x minus 10, so it should be somewhere with this mean and this variance, right? And we'll continue to sample the entire function. So we might sample the red line here, as you saw, or the blue line or the green line. Okay? Once we sample the function, we sample one function and then we choose the optimal point for that function. Okay, so we sample the function and we compute the optimal point for that function. How do we compute that? There are different ways to do it. You can always just randomly pick some points and then see, well, in any case, you computed the entire function, right, in various points, so you can just take the maximum. There are also more sophisticated ways to do it in very large spaces where you don't actually have to sample that. There are like ways to do it parametrically, how to compute a parametric Thompson sample, but we won't go into that. The idea here, the general approach here of Thompson sampling is actually very powerful and can be used in many cases, right? Many cases you might require you to think a bit, but you can adapt them and use Thompson sampling in order to compute or decide on your next point. Okay, so you choose one function and then take the optimum of that function. That's known as Thompson sampling. Okay, so some extra reading. The extra reading, actually, I included here some interesting YouTube talks, YouTube videos that describe the different techniques that we discussed in more detail or from a different perspective. So this might be very interesting if you are if you would like to learn more about black box optimizers, specifically the black box optimizers that we discussed in this lecture. Next, we're going to discuss question.
Are any of these methods popularly used?
Yes, they are popularly, they are used quite extensively, specifically CMA, yes, as I said. Before CMA is used also in state-of-the-art applications, and also Gaussian processes and Bayesian optimization. In some spaces, it's highly effective. Next, our next lecture will cover curriculum learning. So that will be a lecture. This is the expertise of our TA, Vaibhav. He will provide the next lecture about curriculum learning. Assignments, well, you're done. Quizzes, we're done. And project is just your final report that is due by the end of the semester. And that's it. We only have one more lecture. Thank you.